Okay, so welcome back everyone after the morning session of several talks on DESI and eROSITA. Now we are going to start our post-lunch session. So uh, now we are going to hear about cosmological results from the first eROSITA All-Sky survey by Emmanuel Artis, who is a postdoc at Max Planck Institute of Extraterrestrial Physics, and has kindly agreed to give this talk on very short notice. He has been working on multi-wavelength studies of AGN and black hole, covering from radio to X-ray for quite some time. And today he's going to tell us about cosmology results from eROSITA. Emmanuel, over to you. Thanks.
Yeah, so thank you very much for this very nice introduction. So as it was said, I'm more or less replacing Joan Compara, but who has like a problem, and it's great pleasure to be here to talk about the cosmological results from the first eROSITA Sky surveys, and in particular the results that you will get from cluster counts, cluster abundance in the Western galactic hemisphere. So first of all, I'll need to give a brief introduction about cluster count cosmology, because this is basically the main subject of this talk. So here you have a picture of the cosmic web with nodes, voids, and filaments from the TNG simulations. And at the node of the cosmic web, this is where you basically find galaxy clusters, mostly form of dark matter, hot gas that we observe in X-rays, and a few percent of galaxies. And then if you forget about the cosmic web and if you just detect those clusters, and if you sort them per unit of mass and redshift, then you get a nice summary statistics that is very sensitive to the cosmological parameters, and in particular to sigma 8, the root mean square density fluctuation in h minus 1 megaparsec, and also the matter density parameter omega m. It's a very nice statistics because you can also probe the masses of the neutrinos, for example, and also some alternative gravity theories. And this is the main cosmological probe of eROSITA that I will describe in this talk. So talking about eROSITA, before talking about eROSITA, why cluster abundance in particular is very interesting. It's basically for multiple reasons, but one of the most interesting one is the so-called SA tension. So on this slide here, I'm showing you from the paper, the review from Abdallah et al, different values of S8, which is a combination of omega m and sigma 8 that you obtain on the top of this slide from the cosmic microwave background. And what you do obtain if you compare, if you go down, like with the weak lensing from kids, for example, or DES, your 1 or your 3. And what you see here is that there is like a slight, very, very, like a small, not very significant, I would say, tension of between what you would get, what you're getting from the CMB and what you get from the weak lensing probes. And on the bottom of this slide, what I'm putting in red here is what you get from cluster counts. So you see that there is like this slight tension between the CMB and the weak lensing shear measurement, and you would like to know if this is also something that you will get with cluster counts, which is totally different probe. And this is very interesting because of also because of this slide here. So this is on the left part of this slide. What you can see is something that I adapted from a paper of Glaston et al. Like 2023. And it's basically the redshift and scale sensitivity of the different cosmological probes, right? So from blue to green, you go from the linear regime to the non-linear regime. So when you're in the large scales, then you're really like in the linear regime, you understand the physics. So like large scales and higher redshift, you have the primary CMB. And as you go down, you go to low redshift. And if you go to the small scales on the right, then you have like a different nonlinear physics that is going on. And this is very interesting because, for example, the weak lensing shear that is showing like this this tension, I would say, between like the CMB the weaknessing shear, you can see that they're really going into the nonlinear regime, like the weaknessing in the Lyman alpha forest. And what you see is that you have the eROSITA, the cluster sample from eROSITA, which is in red in this slide, and that is very sensitive to the large scales and the low redshift. So this is very like a different span in the redshift and scale sensitivity. And you would like to compare the scales with what you would get from the weak lensing. And I guess it's also very interesting because I know it's a DESI and eROSITA joint symposium, and I also put the cluster in there. And you can see that they're kind of not totally covering the same kind of space. And it's really interesting to kind of ask yourself the question, if the discrepancy are to rise, it's important to test them everywhere to see if you have the same physics at different scales. So this is one thing. And now, as I was saying at the beginning, let's go back to eROSITA. So you had like a nice presentation from Emmanuel in this a couple of hours ago. So I will go very fast on this, but just quickly again. So eROSITA, it's an instrument about the SRG telescope, the Russian-German SRG telescope. We had like 8 times 6 month surveys with an expected lifetime of 7 years, right? So I will not go into the details. You heard from this already. But just like a few order of magnitude, it's like 20 to 30 times more sensitive than ROSAT. And but it's really designed to scan the full sky and deliver like the full sky survey that is going to give you the cosmological results that I will talk about in a few moments. So let's move on. So as you saw this morning, the launch was in 2019. Then ERAS one was taken in 2020. We went up to ERAS 4.5. And then since then, eROSITA has been in safe mode due to the situation, the war in Ukraine. But we have plenty of data that we can analyze and with which we can do cosmology. Okay. And today I will be showing you the results from ERAS 1 only, which is the first that I released, so 1/8 of the final depth that we would have attained at the end of the survey. Okay, very nice. So this morning you had the description of the cluster catalog, of the general catalog, sorry, and now I would like to tell you like a bit more about especially the cluster catalog extended sources. So this was described in Bulbul et al. 2024, and at the end of the day, we have 26,000 cluster candidates in the Western galactic hemisphere only, so the German hemisphere of the sky, with a total effective area of approximately 13,000 square degree. So this is like only cluster candidate, and of course, you know that you have like a agent contamination, background fluctuation. So you need to clean this catalog to remove all the spurious sources and get the completeness and purity, the threshold that you want to actually perform your cosmological analysis in a proper way. So this is the work that was done by Matthias Kluge, you can see his picture on the top right of the slide. So we had like optical follow-up from Liga CDR 9 and 10. Okay. So on the right side of this panel, you have like a nice cluster observed in India 10, sorry. And so you have the galaxies in red and the X-ray surface brightness in white. Okay. So this is very important to do that, as I was saying before, because it's really like increasing your purity. You clean the catalog, and it's also giving you photometric redshift because we don't have like the redshift, of course, from X-rays only. And you also have, at the end of the day, an additional mass proxy, because one of the bottlenecks of cluster cosmology is to get the mass of the cluster that you're looking at, because you want to sort them per mass and redshift. And this additional mass proxy is the richness, an estimation of the number of galaxies that you would get in a given cluster. And this is like on the right side of the slide, you have like on the y-axis, you have the lambda, so the richness. And on the x-axis, you have the velocity dispersion. And you can see the nice correlation. The more velocity dispersion, the more richness you have. And so you have like something that is correlated with the mass. So basically 3 things: optical cleaning, photometric redshift, and additional mass proxy. And if you do this cleaning method, you lower your number of objects to 12,247 clusters with redshift measurement and 86% purity. So that's one thing. Now, if you want to have like a rough idea of the numbers, so on the left part of the slide, you have the number of confirmed clusters against the redshift. So you have like you can compare it with eFEDS, eFEDS, which is like the deep eROSITA, the first deep eROSITA survey that was published a couple of years ago, and you can see. So on the white, sorry, not the white, the yellow histogram is ERAS1, so the full catalog. The orange histogram on the left is the cosmology sample. So I didn't describe the cosmology sample yet, but I will come to it. So it's a purer sample, let's say, but I will come to it. And on the right side, you have like the matched clusters between eROSITA and the other surveys. So you have ACT DR5, which like approximately 1,000 matches. You have the Planck sample in orange, you have MCXT, SPT, and also eFED with 63 clusters. So as I was saying before, now we have like this sample of 12,000 clusters, but of course it's not, I would say, pure and complete enough so that we perform cosmology on it. So we need to actually do additional cuts. And before going to this, I have to tell you that so the XK observable, because again, when you want to do cosmology with clusters, you need like an observable that is correlating with the mass. So in the case of the ERAS1 sample, our observable is the count rate, the number of photons that you receive per second. And this is the thing that we will be correlating with the mass from the X-ray side. So here on the left part of this slide, you have on the x-axis the M500, the mass of the clusters, and on the y-axis the count rate that was observed for all the clusters in the sample. So you can see this nice correlation, and so this is basically our observable. And now quickly, yes. So the second thing, sorry, that you need, like the second ingredient that you need, is basically the number of objects the fraction of objects that you will detect. Because of course you don't detect all the clusters, you detect only a fraction of them. You have contamination, so you need a measurement of the fraction of objects that you detect. And this is basically the selection function. And this thing was actually performed based on simulations that were done by Joan Compara, which was supposed to give this talk today, and Ricardo Sepi. And what you see here in this slide is basically the simulation that they perform. So on the top, on the right panel, you have the n-body simulation, so the light cone, like between, so you have the redshift, so between 0 and approximately 0.7. And so you have the largest system, so AGN and clusters. And on the bottom, you have like the projected version of these light cones. So the black points are basically photons, and you have like clusters in red, AGN in blue, and stars in green. And the most important thing that I would like to say with this slide is that those are the simulations performed by Joan Compara. So you can look at the paper that I presented here, on which we run our detection pipeline to actually know the fraction of clusters that we will miss in the cosmological analysis. So you can see here, for example, the completeness on the left side against the input flux. So you can see, and the different colors correspond to different exposures. So of course, like if you have low exposures, you have like low completeness, which is normal, and then you can go up as you increase the exposure time. And it's basically the same on the right side with the completeness fraction of AGNs there. Okay. And you have like this quantitative for different elements. So you have the spurious fraction on the top left, the contamination on the right for AGNs, and the same for clusters, spurious fraction contamination. Okay, so we're using these simulations to actually get, as I was saying, the fraction of objects that we will detect, which is like our selection function. So once that was done, this is the work that was performed by Nicolas Claire. So we basically used like a Gaussian process classifier to actually compute for the given object with different flux, different exposure times, different hydrogen column densities, and the different count rates, the probability for these clusters to be detected at the given points in the sky. So this was, as I said, this was performed by Nicolas Claire, and on the left part of this slide, you have on the y-axis the probability of detection at a given flux. Okay, so the higher the flux, of course, the higher the detection probability, and you also have like the redshift. So 0.2 is the not the dashed line, the full line, and 0.5 is the dashed line, and different exposure times also between the black and the blue. And of course, as you increase the exposure time, you increase the probability of detection. So we have like this selection function that is well calibrated on the simulations that were performed by Joanne. And so we of course believe that we understand well the selection function of our clusters, and so we can move on to the next ingredient that is needed for cluster cosmology. And this selection function was actually tested also. So we didn't only fit it with our Gaussian process classifier on Joanne's simulations. So here we tested it on external data sets. So what you see here is so we use the EFED, so the deep, the local deep eROSITA survey to actually check if our probability of detection was actually working properly. So what you see on the y-axis is the flux in 300 kiloparsec, and on the x-axis you have the redshift seen in EFEDs. So the color map corresponds to the probability of detection as computed by Nicolas. And what you see is that as you go, and so you have all the clusters, which are basically points, and match detection, so clusters that are at the same times in ERAS1 and in EFEDs, which are circled in black. And what you see here is that, just to give you like an overview of what was performed, the higher the detection probability is, the more likely you are to actually be matched. So basically, this means that we're kind of confident in our selection function, because we see that I will not describe exactly what that was done. You can look at Nicolas' paper, but the higher the detection probability is, the more you have matched objects. So we're kind of confident in our selection function. So just to finish, so I was telling you before that we had like a cluster catalog of 12,000 objects, but actually we wanted something that is pure. Okay, so we actually also decrease again the number of objects. So for example, here you remove the galactic plane, and at the end of the day, you go down to a number of objects which is like 5,263 cluster candidates with a total effective area of 12,000 square degree and 95% purity. Okay, so you can see on the left side of this slide the full survey area. Okay, you have the different weak lensing follow-up surveys that I will go to in a moment, which is HSC, DES, and KIDS, because of course you need to calibrate your observable to the mass. So the way you're doing that is that you're doing weak lensing. So we're very lucky in ERAS ones, we have like these three weekend sales survey, which are kids, DES and HSC. And just to give you an order of magnitude of like the size of this catalog, here I'm showing you the catalogs, the size of the ERAS one cluster sample compared to different, I would say, ICM selected samples, so X-ray and SD. And what you see, for example, like you have SPT, Planck, the Planck sample, XXL, the C1 sample, and CCCP. And you can see that we're basically one order of magnitude higher than what was done before. I think I didn't include the latest SPT results, but we still have like more clusters, which is like, and of course the number of clusters is the leading statistics that is giving you like constraining power. So it's a really, really powerful sample to do cosmology, which is really pure, for which you have like a good understanding of the selection function. So it's very interesting to see the results. So let's move on. So as I was saying before, we have two observable, which are the count rates, which is our main observable in X-rays, and also the richness, an estimation of the number of galaxies that are belonging to a given cluster. So in order to calibrate these relations, these relations, we have three external surveys, which are Dark Energy surveys, the kilodB survey, and the hyperspectrum, which are overlapping eROSITA. This is great because DES gives us like approximately 2,000 tangential shear, KIDS 96, and HSC 236. Okay. So, for example, like in the case of the Dark Energy survey, this was like a tremendous job that was produced by Sebastian Grant this year. So you have like on this slide here, you have like the different reduced shear, okay? And the more you're going to the right, the more you're basically increasing the count rate, okay? So you basically increasing the mean mass. So you can see that you're changing you're increasing the shear profile. And the more you're going to the low panel, the more you're going to the higher redshift. So you can see how the shear evolves as you go to the higher redshift. So of course, you increase the errors. But the most important thing to remember here, the message is that each individual shear for every clusters, every of the 2,000 clusters that we measure with DES, is basically directly injected in the likelihood in order to calibrate at the same time the relation between the count rate and the mass and the richness and the mass and get the cosmology parameter. Okay. So quickly, I'm just showing this slide just to fix the ideas. So it's basically the fit of the different the parameters of the relation between the count rate and the mass. Okay. The blue ellipse were obtained by Sebastian, right? So when he's using his reclancing data, so you have like AX, which is the normalization between the count rate and the mass, BX, FX. I will not describe the different parameters, and sigma X, which is the scatter. And you can see that basically there is like a good agreement between that and the work that was done by HSC on EFEDS. But all to say that the weak lensing measurements are really what is helping us to calibrate the relationship between our observables, count rate and richness, and the underlying mass. And also there is a last thing that is very important. It's basically the bias. So the weak lensing masses that we obtain from the shear profiles that we have like from the weak lensing surveys that we're using are basically biased. And this bias is calibrated also on simulations. So here you have like the value of the B weak lensing, so the bias with respect to the redshift. So the weak lensing simulations, which are in black here, compared to the eROS simulations, which have more details in Sebastian paper. the most important thing is to remember that between 0.1 and 0.8, we have like a bias between 5 and 10% approximately. So this is something to keep in mind and that we're incorporating in our likelihood analysis. Okay. A very last thing before jumping to the results is basically the contamination fraction. So I made a lot of efforts at the beginning of the presentation to explain that we wanted to have a cosmology sample that was pure, that was cleaned due to optical cleaning, and that was reliable to make our cosmological analysis. But it's of course impossible to remove all the background fluctuations that you misinterpret as clusters, and also all AGN that you misinterpret as clusters. So, in order to do this, in the Vittorio Ghirardini's paper, which is like the main cosmology paper that I will present at the end, you have like a mixture model that is taking into account the contamination fraction. So you have like, when you compute the average number of clusters, you account for the expected contamination fraction that you get from Joanne's simulations that I showed at the beginning. And at the end of the day, here you have so this is like the slide taken from Vittorio Ghirardini's paper. And so the best fit model is here, like on the top. So it's the blue line. Maybe it's a bit difficult to see. The clusters are in orange, so they're very similar because most of the objects are clusters, of course, because we made a lot of efforts for that. And we also fit the AGN, the number of AGN, and the number of background situation here. And you can see that we are, pretty satisfied with the model. Okay, great. So at the end of the day, like a small summarize like the method. So basically, you have like an X-ray cluster catalog, okay? Weak lensing shear profiles in order to calibrate the relationship between your observable and the mass. You have a selection function that is based on Joan-Compara simulations and also the Gaussian process classifier that we're using to compute it each step in the likelihood. And we also have a theoretical modeling of the halo mass function, which is just giving you like the number or density of dark matter halos per unit of mass and redshift. Once you get the X-ray cluster catalog, you clean it, and then you have your analysis pipeline, and you can get to your cosmological parameters. So this is like basically the overall scheme that I was presenting before. And I think now we can jump straight to the results. So here, just to make like the summary slide, you have what do we fit at the end of the day? We have the cosmology here in red. We have the X-ray and richness scaling relations. So you have your observable, and you need to fit them at the same time using your weak lensing shear profiles. So this is in green. And you have your weak lensing mass calibration here, which is in blue. And the last thing, you have your contamination modeling, so the fraction of background fluctuation that you misinterpret as clusters, and the fraction of AGN that are still there in the catalog that you also misinterpret as clusters. So mostly, these are the main parameters that we are interested in. Okay, so what do we get at the end of the day? So this is like this slide here. So you see the cosmological results that we obtain, like in the omega and sigma 8 plane. You have the ERAS1 lambda CDM case, which is in orange. You can compare it with other cluster sample, mostly, for example, the one obtained by SPT, so the paper of Sebastian Bocquet 2024, which is in pink here. You can also compare it with like the Garel et al., which is an XXL sample, and which is the XXL sample, sorry. And basically what you can see is that we're consistent with the cosmic microwave background. And yeah, so which is good news. And if we combine ERAS-1 and Planck, you get the red ellipse that is in the middle. So of course, all of these errors are 1 and 2 sigma errors. So yeah. And so we get an omega m value, which is 0.29 with 7% precision, and sigma 8, which is like 0.88 with 2% precision. So we did not stop there because at the end of the day, you of course can extend this. So you have like also, you can vary the dark energy equation of states. And in this case, you can see that the eROSITA results, which are always in orange in this slide, are are quite competitive. So you have like -1, which is like the lambda CDM value, and you can see that our best fit is -1.12, which is of course like very interesting in light of the latest DESI results. And we have like the Planck CMB, which is in orange. And long story short, like we are able to measure the dark energy equation of state to some kind of relatively good precision in the omega m W plane with our clusters. Last thing are the neutrino masses. So, of course, as I was saying at the beginning, clusters not only measure omega m and sigma 8, they're also very sensitive to the sum of the masses of the neutrinos. And if you apply our method, what you see is that we are able to measure the sum of the masses of the neutrinos to 0.22, about something that is minus 0.22 electron volt with 95% confidence level, which is great. And you can compare it with what was obtained on the left side here with SPT in green and Planck in blue. So if you combine Planck and eROSITA, then you get the red ellipses that is on the bottom here. So it's actually like a very, very interesting results. So one of the most interesting thing also that was actually found with with the eROSITA crystal sample is that at the end of the day, we do not find the same tension as the one that is observed with the cosmic shear, for example. So if you look at our S8 value here, you can see that the CMB here is in the middle, not on the top. So on the top you have clusters, in the middle you have the cosmic microwave background. And if you go even lower, for example, if you look at the DES cosmic shear or the cosmic shear in general in purple, what you see here is that we are on the right side very consistent with the CMB and even a bit higher, but still very, very consistent in terms of statistical measurements. So the gray area here is ERAS-1 plus Planck, and you can see that we're very consistent with the cosmic microwave background. So again, the question that is connected to this finding is really like whether it's something related to the scale. If you remember the plot that I was showing at the beginning with the different scales, the different redshifts, or if it's related to something else, and this is something that has to be that is under investigation. So I think that's mostly it for the main cosmological results of eROSITA. But I didn't want to leave you without maybe a broader overview of what was done, because we didn't stop there with only the lambda CDM case. We also have a bit more, which is the cluster 2-point correlation function, for example. So this is a work that was done by Riccardo Seppi, who did a tremendous job with that. So he was also involved in the simulation. So basically, you have a volume limited selection of the ERAS-1 cluster sample. And his main goal here was to study the HOD model in clusters with with the 2-point correlation function, basically. So you can see the different volume limited sample that he used. I mean, you can have a look at this paper if you want more details, because I won't have time to go into deep details on that. But here you can see the projected correlation function. Of course, it's a bit translated so that you can see it in the different volume selected samples, okay, for clusters. And briefly, one of his main results is that because like we're still interested in cosmology, so of course his goal was to study the HOD, but here I wanted to focus on what he gets for the cosmology, and it's basically here on the omega and sigma 8 plane. So you can compare this with different other clustering analysis. In purple, you have kids. In red, you have codex. And in blue, you have eROSITA. And eROSITA counts in green. So maybe you were wondering why our results are so large compared to codex or to kids, but the result is really that this study was designed to actually study the HOD model. So they were free in this analysis, while the other people basically set them fixed. So of course, if you were to fix them, you would be like really aligned with like the purple or the red contours. Okay, but it's still a pretty impressive result that we were able to fit the HOD and the cosmology at the same time, and it's really a good news for the future data release when we will be combining our clustering analysis with the cluster counts experiment. Okay, so there is like even more just before I leave you, because I don't think I have a lot of time left, but I wanted to talk a bit about other stuff that we did, which is about gravity. So we basically also use the clusters to constrain like another like a modified gravity model. So basically the main idea in this case is that you basically change your Einstein-Hilbert action. So you, instead of having the Ricci scalar there, you just have like a function of R. It changes your Einstein equations, okay? But without entering the details, really just to show think quickly. This function R, what you're trying to measure when you're doing this is that you're trying to measure this parameter FR0. If it's 0, then you're basically in lambda CDM, okay, nothing too special. And if it's different than 0, then you're trying to see like a deviation, something that doesn't work from lambda CDM. And this is very interesting because at the end of the day, if you change gravitation, then you change the halo mass function, you change the number density of halos that you observe, and you also change the gravitational collapse of structures, okay? So basically clusters are really the right probe to try to see if you can see any deviations. So this was done before. So here I'm showing like a paper from Cataneo, it's like 2014, and you can see that clusters, when they're combined with the CMB, the supernova, and the BAO, you can really see like this nice linearity between FR0 and sigma 8, and you're really able to constrain the log 10 of FR0. Just to give you a brief overview on that, what does it do to the halo mass function? So if you increase FR0, you basically go from the black curve to the yellow one. So you increase the number of halos at the number of massive halos, okay? So if you increase FR0, you increase the number of massive halos. So what do we get from the results? So I will not, again, it's just to give you like a brief overviews. On the left side here, what you see is the omega and sigma 8 contours that were obtained from the main analysis in gray, and what you obtain in the F of R model with the sum of the mass of the neutrinos fixed. Okay, so you can see that of course you increase the size of the contours, which is expected. But more importantly, what's important here is to see that you're able to constrain the log of FR0 with clusters only. So if you remember, I will just go back a bit quickly. But if you remember, the study that I showed you here was obtained with clusters combined with the CMU. But it was done only for a couple of clusters. So now that we have 5,000, we're able to do it only with clusters, which is very interesting because we do it in a consistent physical framework. Because of course, like If you combine it with the CMB, you make a lot of assumptions on the physics, and if we're trying to see like a bit of deviations, it's very cool that we're doing it from end to end in a consistent physical framework, and this is exactly what we did here. And it's also very encouraging for the next data release, for which we will have more statistics, more data, and maybe a better mass calibration. And you can really see that we're able to constrain this log of f about 0 with clusters only. And also, we also computed the S8 in this model, and you can see like ERAS1 lambda CDM in gray, Planck in green, and F of R with the sum of the mass of the neutrinos, which is fixed, and 3 in pink. And you can see that all of them are really compatible. So still compatible, so nothing particular to say regarding the S8 tension in this case. So we're reaching the end of this presentation. So I just wanted to, before finishing, to show you what's next and what's going like in the next month for the ELAS one, because now I think we analyzed most of the data in terms of cosmology. So we will be moving to the next step, the next data releases, and we have a lot of work to do. But we wanted to understand a bit more why we could not say why we couldn't see any trace of the S8 tension in our cluster sample. This is like an interesting question. So what we did to do that is actually to cut our sample in different redshift bins and redo the analysis in each one of those bins. The reason why we wanted to do that is to see, is to kind of capture the growth of structures with redshifts in our sample. And we can do that because we have a lot of objects. We have like 5,000 objects, so cutting the sample in 5 redshift bins is still very possible. So on the left axis, on the left part of the slide, sorry, you have like the redshift and log of the count rate of the different samples that we cut. So we have 5. And the way we cut them is that we wanted to just to make sure that we have the same number of clusters in each one of the bins. Okay, so it's an arbitrary way, but it's really to kind of get the same basic statistical power when we are cutting the sample. So on the right axis, you have the same plot approximately, but you have the number, like the histogram of the objects with the redshift. And just to give you like a quick preliminary view of what's happening. So basically you have the crystal abundance that we we decided to combine it with the sun horizon. Why with the sun horizon? Because it's an extremely, something that is very difficult to doubt. Everybody believes the sun horizon from the cosmic microwave background. So basically, you can have those pliers. And what you can see is that you have the 5 first bins, okay, as well as the last one, which is a bit surprising, which is a bit higher. But at the end of the day, if you compare it with what everybody's finding, you see that usually, so you have like this from Abbott et al., so that's DEF, and you can see that usually people have like around like 0.7, 0.8. People have usually higher value of sigma 8, so this is something that we kind of expected. And also, for example, in this slide here, when you see that like people have a bit of a higher value at around like 0.8. So yeah, so this is something that we kind of expected. And at the end of the day, if you look at our results, you have the sigma 8, the omega m, which is mostly constrained by the sun horizon, and our S8 value. Okay. And just quickly, because I'm running out of time, so I will conclude. So you have like the sigma 8 of Z, which is like the red line here, that is obtained from Planck 2018, BIO, and also supernovae. Okay. You can so here you can add on top of it, for example, the DES frequency here, and also like the some LRG analysis, 2.2, plus the CMB. Okay, so you can see that basically people are usually lower. And you can compare this with what people obtain with clusters. So basically, this is the same plot, but what we obtain with clusters only. So you can see like the one from the analysis of Sebastian Bouquet, like SPT in orange, and what we do obtain in ELAS1 in black. And you can see that you start to see that maybe at the end of the day, the sigma A tension might be like a scale problem. Maybe because at the end of the day, we are kind of in good agreement, except for like one bin, which is a bit higher, that we kind of also see in SPT. We're basically in good agreement with the CMB. And if you do the full plot, you can see that there is really this difference between DES, the cosmic shear, the LRGs, and for example, what you would get with clusters only, which is either in orange or in black. And that's very interesting. And I think it's kind of bringing like an interesting light on the S8 tension at the end of the day. Maybe in another parameter space than the one that people usually saw in the omega m sigma 8 plane. So yeah, so that's it. I think I will leave you with my conclusion like quickly. So basically, I think I wanted to show you like the results, the latest results from the eROSITA, the first eROSITA Sky survey. The most important thing is that we're measured omega m with 7% precision, sigma 8 with 2% precision. So for clusters only, I think it's the largest catalog. ICM, well, we selected with ICM, of course, because in optical they have bigger catalogs, but that's another story. We have also the sum of the masses of the neutrinos, which is measured like competitively. We do not find traces of the S8 tension. We have like a lot of satellite results. I showed you like two of them, the one of Ricardo, Sepi, with the cluster clustering and the HOD model, or the one with F of R gravity. And we have more results to come on the growth of structures. And yeah, I'd say thank you for your attention. And yeah, I leave you with this conclusion.
Thank the speakers. Thanks a lot, Emmanuel, for that detailed overview of eROSITA cluster cosmology. Do we have questions?
I had a question about the earlier part of your talk where you talked about actually selecting the clusters. So you mentioned about 26,000 cluster candidates, and then you go to DESI for the redshift. So is it that you select sources, extended sources above some surface brightness density, surface brightness, and then fix them as the candidates, and then go to DESI for redshifts, and then if you find some minimum number of galaxies for each, then you determine that that is a cluster? Is that how it is? Or
I mean, roughly, if I understood your question, roughly yes. The main thing that we do is that so at the beginning, it's the same. I think that Andrea Merloni described how you basically select the extended sources in general, and basically you go down in numbers. So the first thing is that you have like a richness threshold, for example, because some of the fluctuations that you detect as clusters, they don't have like a richness optical counterpart. So then remove those that have no galaxies, basically, with a given threshold. I don't remember how many exactly. So basically, you lower the number. And yes. And I think for the next step, it's also like you have the cosmology sample which has like a higher extent. I mean, basically the higher probability of having extended source is like it's basically purer, and so it's basically here. And you also remove the part of the galactic plane, which has basically a too big hydrogen column density. So at the end of the day, that's basically it. So you remove, like, I think for your specific question, it's mostly that you remove the things that are detected as clusters, but that don't have galactic counterparts, optical counterparts, sorry.
I guess your question was about how do you use a photometric thing, right? So I think
Well, so do you have a minimum number of spectroscopic redshifts of galaxies that you require to identify a given source of the
So
cluster?
so we are only, I mean, in this case, we are only using photoses. So maybe it's a bit misleading, but we're doing like we're using the legacy of VDR 9 and 10, so we only have photoses like for clusters. And as you were saying, for these photoses, we are again like we have a minimum number of galaxies beyond which we're removing all the objects. So if you have like less than, I don't remember the number exactly, but let's say like if you have less than it's not a large number, less than five galaxies, not five, like less than a few galaxies, then we don't consider it as a cluster, and we will remove them from the catalog.
so just to add to Emmanuel, what Emmanuel just said, this doesn't require a spectroscopic redshift at all. These are all just imaging surveys, and DESI also has an imaging survey. Maybe that's why you're confused. That legacy imaging survey is talking about is just the images without any spectroscopy, and they're just counting number of galaxies around the clusters, and that gives the richness. Shabir?
Hi. These sigmoid constraints obtained from cluster counts, how sensitive they are to modeling of baryonic physics within clusters?
So they're indeed within clusters. So they're indeed sensitive to this because, for example, we have like an ICM selected sample, which means that we're selecting the object based on the gas. So of course, if you change a bit the physics of the gas, for example, the profile that you fit, it will change the sigma 8 values, but we really did our best to avoid too much baryonic dependence, because that's why, for example, we're using the count rates, which are only the number of events that you receive per second. We could have decided to fit like something else, like the gas mass, for example, but we really wanted to have the quantity that is the closest to the data with the less implication from the baryonic physics. So you do have a bit of an effect, but something that is supposed to be minimal because of the modeling choice that we made. But just to say quickly, to go a bit more in your direction, there are like other things that indeed can have an impact, which is the fact that, for example, the halo mass function that we're using, that is based on dark matter n-body simulations only, does not have like baryonic physics in. It's not supposed to be something that is, the leading source of systematic effect, but I mean, there's still an effect there somewhere. And there are people that showed, like, for example, if you have an impact, people at Sebastian Bokeh and the baryonic physics on the dark on the halo mass function, but it's not supposed to be dominant. So, long story short, to answer your question, there's supposed to be an impact, but the effect is very small. But on the other hand, it's appearing at every step in the analysis. But it's supposed to be not dominant because of the modeling choice that we made.
Thank you.
Hi, thanks for the talk. So I had a question about the Hubble constant. Do you measure the Hubble constant in your data, and do you have anything to say about the Hubble tension?
So you have a very good point. So in this data set, like first clusters counts usually are really not very sensitive to the Hubble parameter. So you don't get any constraints from that. So long story short, no. But in this specific case, this is kind of why we decided to, if you look at the value here, we have like the expansion rate, which is the prior is basically 67.77 with like sigma 0.6, which is like basically fixed. So, but we did that because clusters are not sensitive in any way to H naught. And in any case, if you look at the appendix of the cosmology paper, we also did the case when those pairs are like way larger than that and it doesn't have a huge impact. So yeah, so I don't have anything specific to say because basically we don't measure it. And I think in any case in the future, the baseline will be to have like a basically have it a bit more free, just to avoid confusion because at the moment at least we do not measure it.
Okay, thanks. Just one other question about the equation of state. You had one result saying that in the equation of state for dark energy, you have an estimate for W, right? In the DESI survey, as far as I understood, they use this 2-parameter equation for this equation of state and try to claim that the dark energy is it's evolving, right? This W is evolving and so on. Do you also try and fit this to a 2-parameter thing and see if your results match with the DESI ones?
So we indeed tried, but we decided not to include it directly in the paper for many reasons. The main being that we already know that we're starting to reach the best of what we can do, and if we go a bit further, we will start to be dominated by systematic effects, and we need to improve. We have many things that we need to improve already, even though like what we did we did our best to have like a good selection function, but we know that we have things that need to improve, and we didn't want to actually go too far into speculation with the dark energy equation of state, but because we have things to do before that. But to answer your question, if you look at the value of the dark energy equation of state that we have already, like even if it's fixed, it's not the Chevalier-Polarsky parameterization, like W is W0 plus 1 minus A times WA. Like this is already like a bit lower than, our best fit is lower than -1. And what I can tell you right now is that if I remember when we did the test back in the days, we indeed have things that go kind of in the same direction. But indeed, like it's, I mean, it's a work for the next data release, I would say.
Thanks.
So I think I missed this, but do you also have a spectroscopic follow-up campaign to measure the velocity dispersions of clusters? And so with the baryonic mass which you get from clusters, you can also do things like baryonic Faber-Jackson relation between the cluster and also for the BCG. So is there such a plans?
So to my knowledge, and of course I might, I remember quite a lot of the projects, but I might forget one. I do not think that we have some kind of follow-ups going on at this very moment. But of course, like this is like a great idea and something that should definitely be done. But we do not do this at the moment. If just to clarify, I did show this plot here with like richness versus velocity dispersion, but this is not part of like a direct.
So richness is proportional to, I think, the total mass. What I'm talking about, just the baryonic mass. So Yongtian has found a very tight scatter.
Yeah. No. But I think you're very right. But the short answer is no, we do not do that at the moment.
Okay, so let's thanks Emmanuel again.